Okay, good morning, everyone. Last class, we discussed some types of printers, dot matrix printers, inkjet printers, laser printers, etc. We'll just go through some of the data acquisition systems. In fact, we did some of these DAQs in our signal conditioning chapter. Okay, we'll just quickly browse through the data acquisition system, because remember we are into the data representation element. So in the data representation, we studied display elements, we studied some printers, recorders, and then finally we'll just browse through some data acquisition elements, because nowadays in mechatronic systems, it is not just the display of the data that is important, or it is not just the recording of the data that is only important, but today we have microprocessor based control systems, we have microcontroller based control systems, and we have computerized monitoring systems. So in such a situation, whatever conditioned signal that I have, or whatever data I have accumulated through my sensors, transducers, that data is needed to be given to a microprocessor, and microprocessor processes that data, or microcontroller processes that data, or a computer processes that data, and it suitably modifies that data, either by using some data processing algorithms so that it can be made more meaningful. Nowadays, this data science is in much demand, because whatever data I'm getting through my transducers, whatever pressure data I have got, air quality data I have got, air velocity data I have got, I should be able to process that data in a systematic way and represent that data, or project that data, present that data in a meaningful, conclusive format. So there also I require some data processing elements, and in that we have data acquisition systems as one of the elements of my mechatronic systems. Let us quickly, we have seen this, we'll just browse through a bit faster. In a data acquisition system, or DAQ, inputs from the sensors are converted into a digital form for processing, analysis, and display by a computer. The systems thus contain, the data acquisition systems or DAQs contain sensors, wiring to connect the sensors to signal conditioning, to carry out filtering and amplification. So all these acquisition of sensor signal, processing of sensor signal, converting that sensor signal, all these will be categorized under DAQ. So DAQ hardware is used to carry out functions as conversion of input to digital format and conversion of output signals. See, this is also important. It is not just getting the data from the sensors and transducers and processing it and converting it, but after it is being processed, whatever control signals I want to generate, whatever actuating signals I want to generate, those output signals, maybe if I'm using a microprocessor, if I'm using a computer, if I'm using a microcontroller, those output process signals could be of the form of digital signal. But my digital signals cannot drive my actuating motor. They cannot drive my electro-pneumatic system or electro-hydraulic system. There I require analog signals. So this DAQ also converts the output signals to analog format for control systems, the computer and DAQ software. Okay. The software carries out analysis of digital input signals. So the DAQ software carries out analysis of digital input signals. Application software like LabVIEW, you must have seen, along with MATLAB, we make use of LabVIEW software, which is of much use. Application software such as LabVIEW can be used to assist in the designing of mechatronic system and the analysis of data. As you can see in the sketch, as I said, all these sketches and this information I have taken from book by Bolton. So that is our textbook, so to say, a soft copy of which I already put on our Google Classroom. So digital inputs and outputs through one port, analog outputs through ADC, and then analog inputs. Now analog inputs will be converted by using ADC into digital form. Then there is a interface for my desktop computer or personal computer. So I have a bus through which this data, all these connections can be provided. Either it is a serial bus or the connecting wire or connecting network, which will feed that data to the computer. So this will be a sort of a DAQ board or DAQ card. So on these cards, all ADCs, DACs, interfacing circuitry, all these things will be there on this PCB, printed circuit board, can be called as a DAQ card or DAQ board. And just like a RAM we put in the slot of a computer, this card, DAQ card, can be placed. So we have a multi-pin socket or multi-pin plug, then connection to computer bus. So there I can put it in the computer slot wherein I can feed that data. Okay, so this is regarding our data acquisition system. Let us move further and let us see a data logger. Now data we have already acquired. You would ask, what is the meaning of this data logger? Now, if typically if I am sitting at AGPAD, in my college I am sitting and I want to control and I want to collect the data, maybe from my IC engines lab, I need not necessarily go to take my laptop or computer and sit there necessarily. Sitting here, I can get the data. Maybe nowadays by using the internet, I can get the data in the wireless format or through a LAN cable, I can get the data. Or in earlier days, what they used to do is that whatever systems I have, remotely placed systems I have, there I used to have this data logger card. So all that data used to be taken on that memory chip, and that card we used to insert in our computer by bringing it here. So that's how that data logger, which includes all my sensors, transducers, signal conditioning, plus data acquisition system, data acquisition card. So this data logging itself means that I'm collecting that data. So data logger is a data collector, data compiler, data processor. So everything is done through data logging system. So from those remote locations, I used to take that data on the card, and then I used to connect it to my PC or my computer, my desktop or my laptop, whatever way it is. So these data logging systems are also data representation elements. The term data logger is used for data acquisition systems which are able to be used away from a computer. Once the program has been set by a computer, it can be put into a memory card which can be inserted into the logger and have the program downloaded to it from a computer, so enabling it to carry out the required data acquisition system functions. As you can see in the sketch, this is the overall block diagram of a data logger system. I have digital inputs, multiple digital inputs. So I have digital multiplexing or digital mux, so to say. Then I have got analog inputs, which I'll be getting from my sensors and transducers located at various locations of a system, of a mechatronic system. Then I have analog multiplexer or analog mux, you can say. What you can do is multiplexing we already studied. One by one, even though I have connected all these inputs to a multiplexer, one by one, as the need is there, I can process that data by using single set of amplifiers, single set of ADC, single set of DAC. So one after the other, I can process the data and feed it further. So this is analog mux or analog multiplexer, and I've got digital mux or digital multiplexer. So for example, I've got thermocouple inputs. I've got three connections or three locations of temperature measurement. Maybe I have a heat transfer equipment, so to say, maybe a convective heat transfer measuring equipment. At three locations, I have these thermocouple sensors. I'll be getting all those temperature signals and giving it to my analog multiplexer. So cold junction compensation and linearization will be done by this block, by this circuitry, and then it will be fed to my analog multiplexer. Now this analog multiplexer, so one after the other, in a sequence fashion, it will give this signal to the amplifier, and then A to D converter. Or if it is a digital signal, this sample digital signal will be directly fed to my microprocessor. If it is an analog signal, it will be amplified, processed, conditioned. By using ADC, it is converted to digital form, then it is given to a microprocessor. And then I have the program input, either using a human machine interface, HMI, or maybe a keyboard, whatever way I'll be inputting the program. Then the microprocessor can be used to control the gain of the amplifier of this analog signal conditioning also. Okay, so this microprocessor will be controlling the muxes also. It will be able to control the digital mux, digital multiplexer, as well as analog multiplexer. So microprocessor can control all the signal conditioning devices at a time. So through a remote control, or maybe I have a transmitter, I have like a Wi-Fi connectivity I have got through my microprocessor, through a controller. I can have connectivity, remote connectivity from a remote place. So all these are provided in the block diagram. And thereafter, after processing all these signals, either the microprocessor will help us in displaying those signals, or microprocessor can help us in printing, getting the printout of the signal, or the microprocessor can help me out in recording or storage of the data, either in a recorder or in a floppy disk. Floppy disk is the old story now. I have a hard disk also, or other systems wherein I can record the data. Or there can be one more output, so that output can be given to the actuator, which we'll be studying in the coming next unit, that is various drives, actuating drives, maybe hydraulic actuators, pneumatic actuators, or electrical actuators. So microprocessor can generate that output signal for those actuators as well. So this is how, this is the block diagram of my data logger system. Okay, that's all in unit 2, friends. We'll move to unit 3. As I said, if you try to recall the overall block diagram of a generalized mechatronic system, we had sensor transducers, we had signal conditioning devices, we had data representation devices, and then we have the controlling elements, and then we have the actuating elements. These actuating elements, as I said earlier, can be your hydraulic cylinders, pneumatic cylinders, or electric motors, maybe a DC motor, maybe a AC motor, maybe a stepper motor, maybe some sort of a solenoid. So all these actuating elements of a mechatronic systems will be actuated through my signal conditioning and microprocessor, microcontroller devices. So this will be discussed in my unit 3, that is drives. In this unit 3, in the drives chapter, we'll be studying some of the electrical drives, some of the hydraulic drives, some of the pneumatic drives. Probably we have already studied the mechanical systems earlier for the last 2 years, various mechanical devices like cam actuators, various mechanisms we have used for actuation. So for that, in our curriculum, in our syllabus, they have included mainly the hydraulic systems, pneumatic systems, and some electrical systems. So one by one, we'll be studying these drives. So to begin with, we have electrical drives. In electrical drives, as I said earlier, these electrical actuating elements can be some switching devices as well. This can be a solenoid type actuating devices as well, or they can be the motors proper, the drive systems proper. In switching devices, we have some mechanical switches like relays, solid state switches, diodes. Diodes are used as solid state switches, thyristors, transistors. Those transistors are also switching devices where the control signal switches on or off some electrical device, perhaps a heater or a motor. So we are not going to study these in details. We are just having an overview of the electrical drives that we come across in mechatronic systems. Then we have solenoid type devices where a current through a solenoid is used to actuate a soft iron core. As we know about a solenoid, I have a winding in the periphery and I have the soft iron core, and that iron core can move in and out, and it can actuate some mechanical device, mechanical gadget, so that I do the intended function. Maybe it is actuating some relay even, or it is moving some load even. So these solenoid type devices or drives are also used in mechatronic systems. For example, a solenoid operated hydraulic pneumatic valve. So these are the pilot valves of hydraulic and pneumatic valves which are actuated through solenoids. So those are called as electro-pneumatic systems or electro-hydraulic systems, where the valve of a hydraulic or pneumatic system is actuated through an electrical system, that is like a solenoid. So, for example, the solenoid operated hydraulic pneumatic valve, where a control current through a solenoid is used to actuate a hydraulic or pneumatic flow. So, a flow control valve can also be actuated by using a solenoid type valve, a solenoid controlled valve. And finally, in the electrical drives, we have drive systems such as direct current motors, we have alternating current motors, we have synchronous motors, we have got stepper motors, we have got induction motors, where a current through a motor is used to produce a rotation. This we already studied in second year. We'll just brush up these electrical drive systems. So we'll be focusing more on the electrical drive systems like DC motors, AC motors, stepper motors in particular. So in the electrical motors, these are frequently used as the final control element in a positional control system or a speed control system. Remember, a positional control system is also called as servo mechanism, wherever the objective is not just to continuously move the load, but the objective is just to change the position of the load, or change the position of a valve, change the position of a switch, change the position of a lever arm. So those positional control systems are called as servo mechanisms. Like, suppose if you studied, we already studied the hydraulic turbines. If we are talking about a Francis turbine, let us say. So Francis turbine is a reaction type turbine, if you remember. So the runner is rotated by the reactive forces generated by the fluid pressure, isn't it? So that reacting ring has got vanes along the periphery, and I have got the runner, that is the rotor runner, which has got vanes or blades. So this the ring at the periphery, which is also called as a control ring, it is rotated in such a way that I generate a jet, so to say. I generate a reactive jet, so that I generate more pressure change, and in the process the runner moves. Now whatever this control ring is there, the angular position of the control ring is controlled through a hydraulic servo mechanism or an electric servo mechanism. What I want to do, I want to change the angle of the vanes of the reaction ring, angle of the vanes, the angle, so angular position I want to change. Earlier it was 30 degree, I want to make it as 38 degree, right? So I want to change the angular position of the vanes of that control ring. So such a system is called as servo mechanism. So there I make use of hydraulic system, sometimes pneumatic systems, mostly electrical systems. So I have electrical servo mechanism. So what is the difference between electrical motor and electrical servo motor? In electrical motor, I'll be continuously getting the angular velocity or the RPM, continuously rotating rotor I'll be having. Whereas in electrical servo motor, I'll be just getting the positional change, not number of rotations. We'll be having angular positional change. So I'll be calling this angular position changing electrical system as electrical servo mechanism, whereas the DC motor or AC motor, electric motor, which is giving me continuous speed and torque, will be called as the electrical motor. So positional control system, in the positional control system, I make use of electrical servo mechanisms, or I'll be using the speed control system for controlling the speed of a electric motors. Motors can be classified into two main categories as DC motors and AC motors. Most motors used in modern control systems are DC motors, simply because their speed can be easily controlled. Whereas in AC motors, the speed, it is a bit difficult and costlier to control the speed of a AC motor. That's why DC motors are preferred in modern control systems because of their controllability, better controllability. And it is possible to divide DC motors into two main groups: brush type DC motors and brushless type DC motors. In brush type DC motor, it has got the coil winding, and the stator can be either a permanent magnet or an electromagnet. We'll be studying this in details in the coming lectures. So in the brush type DC motors, I'll be making use of a pair of brushes on the commutator. We'll be studying the constructional details of this brush type DC motor. So making use of brushes, I'll be giving input current to my armature or rotor. And then the stator, any motor has got rotor and the stator. Stator is a casing and the outer winding, stationary winding. And I have got the armature, which has got a winding on it, which is continuously rotating. So in brush type DC motor, it has got the coil winding, and the stator can be either a permanent magnet. I'll be having a pair of magnets having north pole and south pole, it will be a permanent magnet. Though electrical supply is required there, as far as the magnetism is there, they'll be giving me the magnetomotive force. Okay, so the permanent magnets I can be using for the stator, or I'll be making use of electromagnet. What is the meaning of electromagnet? When the power supply is given, electrical supply is given, the poles are generated, then only it becomes an electromagnet. It becomes a magnet. When the power is withdrawn, when the power is taken out, the magnetism does not remain there. So those electromagnets depend on external power, whereas permanent magnets don't require any external power. So this is brush type DC motor. And one more type of DC motors is brushless type DC motor. In this, the arrangement is reversed. Unlike my brush type DC motor, the rotor is a permanent magnet. In the brush type DC motor, stator was a permanent magnet. In brushless type DC motor, the rotor is a permanent magnet and the stator has the coil winding. Right? The role is reversed. Brushless, there will not be any brushes used for supply of power to the armature. So this is brushless type DC motor. We'll see the constructional details of brush type DC motors in the next lecture, friends, because the next